Hi everyone, welcome to this first lecture on Analog Circuit Design 1. I'm your instructor, Chan Carusone from the University of Toronto.
The material in the videos is taken largely from this textbook on analog integrated circuit design. I played a hand in authoring the second edition of the book, so pedagogy follows closely what we're going to be going through in the lectures here. I consider the material in this first lecture today as background knowledge for study in this area, but it's always good to review and establish a consistent set of notation. Since the focus is on CMOS design, the first part of this lecture will just review the basics of the square law model of MOSFETs and parasitics. Here's a simple one-dimensional model of the MOSFET with which I assume you're familiar. Depicted here is an NMOS transistor, and so clearly when a gate voltage exceeding the threshold voltage is applied between the gate and source, the channel or p-type region under the gate is inverted, creating an n-type channel between drain and source. The resulting channel conductivity is inversely proportional to the channel cross-sectional area, and therefore the resistivity of the channel decreases with increasing the effective because its cross-sectional area increases with increasing the effective. At high voltages between drain and source, the channel cross-section becomes restricted near the drain end, and so as it starts to become constricted in that way, it no longer has a uniform cross-section all along its length here, and so therefore it deviates from a linear voltage current relationship and starts to flatten. Once the gate to drain voltage no longer exceeds the threshold voltage, then the channel is pinched off of the drain end, and we're going to refer to this mode of operation as active mode. It's also often called saturation mode for the transistors, although that can sometimes be confusing since it's more analogous to the active mode of bipolar transistors than the saturation mode of bipolar transistors. At this point, further changes in the drain source voltage have little impact on the drain current as long as this saturation or active mode condition is maintained. So the drain current indeed becomes weakly dependent on further changes in the drain voltage. So we're going to, again, to establish some notation here, we're going to refer to the threshold voltage for NMOS transistors as V subscript T for threshold and N for NMOS, and V with a subscript T and P for the threshold of PMOS transistors. In general, we're just referring to the threshold of transistors. We might just use the symbol VT. V effective, or the so-called effective gate source voltage, refers to the amount by which the gate source voltage exceeds the threshold voltage. And it's best to think of this in absolute terms so that there's not confusion, when it comes to PMOS devices, which, in a typical scenario, have a negative threshold voltage, strictly speaking. So I find it easiest to think about these quantities in absolute terms and keeping in mind the typical polarities that that we have for NMOS and PMOS transistors. That is positive threshold voltage for NMOS, negative threshold voltage for integrated circuit PMOS transistors. So this symbol V effective refers to this effective gate source voltage and is often referred to elsewhere as the overdrive voltage, so we may use those terms interchangeably. So I'll next remind you of some of the expressions that relate the channel current to the terminal voltages in a MOSFET, again using an NMOS transistor as our prototype. Here's the expression that governs the voltage current relationships while the transistor is in the linear or so-called triode region. Okay, and you'll see that the current has a linear dependence on the gate overdrive voltage, or our so-called V effective. And that's again because larger V effectives increase the cross-sectional area of the inverted channel region, thereby reducing its resistivity and and linearly increasing its drain current. And then we also see a term that's linearly dependent on the drain source voltage. That's what makes it behave like a resistor for low values of VDS. But then as VDS increases, we start seeing the impact of pinch off come in. And so this term here introduces the flattening of the I versus VDS curve. So just to be clear, this is the plot of drain current versus drain source voltage with the gate source voltage held constant above the threshold voltage of the transistor. So the channel is inverted. Okay. Now in the simplest model, the current is assumed to remain absolutely constant once it enters the active region and with respect to further increases in VDS. And so with that being the case, we can find out what that value is by equating VDS with the effective gate overdrive voltage here. And if we make that substitution, we see that both of these terms here look like V effective squared. So we've got V effective squared minus half of V effective squared, and you end up with the expression shown at the bottom, which is the classic square law, so-called square law equation, because it highlights the quadratic relationship between drain current and the effective gate source voltage or gate overdrive voltage. And as I said, that was the simplest model. In reality, increasing VDS much beyond V effective shortens the effective channel length, resulting in an increase in drain current. And we modeled this increase in drain current with an additional term parameterized by lambda. And the term lambda is in turn inversely proportional to the channel length of the MOSFET. So here's where you see the impact of that term lambda, and you see that as VDS exceeds V effective, this term starts to increase, and you see therefore an attendant increase in the drain current. This is also a relatively simple model, and you may expect deviations from this model, especially for short channel lengths. However, it does capture a lot of the key intuitions that we need to do analog design. So here's a more complete picture of the voltage current relationships in a MOSFET. You'll see here there are three main regions we want to capture. Actually, there's a fourth one that I'll just start out pointing out, which is that when VGS is less than the threshold voltage, you've got a drain current equal to 0. So there's a curve down here that represents the drain current when VGS is less than the threshold voltage. As soon as VGS exceeds the threshold voltage, the channel is inverted, and then you can distinguish between the triode region for small values of VDS less than the effective gate source voltage, and what we're calling the active region when VDS exceeds the V effective. So the border between these two here is right when VDS equals V effective. Now we're showing this plot here for various values of VGS. So as you go from one of these curves to the other, what's happening is V effective is increasing. And so as it does, the transition between triode and active region also increases. Now also shown here are so-called short channel effects, which arise at very large values of VDS. Short channel length devices exhibit an increase in drain current beyond what's predicted simply by channel length modulation. And that's exhibited here on these plots by seeing the curves start to angle upward. So here we've got this linear relationship between drain current and VDS that's captured by the lambda term in our model, but this extra curving here is not captured by the lambda term. Additional terms are needed to capture these short channel effects. Should also remind you of the body effect. So all of these preceding relationships assumed a body potential equal to the source potential. That is, the source body voltage was 0 volts, but that won't always be the case. The body terminal actually can be thought of as a backgate that works on the channel region in a manner very similar to the main gate of the MOSFET. And that's because the body terminal is doped silicon and therefore conductive and separated from the channel region by a relatively thin insulator, which is the depletion region that forms across the PN junction between an inverted channel and the body terminal. So you've got a conductor, this so-called backgate, separated by a narrow insulator, and therefore there's a field effect acting on the channel that is determined by the voltage between the body and the channel. And the channel potential is quite closely related to the source voltage. So therefore we can model the effect, the body effect, as an increase in threshold voltage, VT, with increasing source to body voltage. The primary model parameters are the Fermi potential of the body and body effect constant gamma, which really parameterizes the relative strength of the back gate's impact on the channel region and the main gate's impact on the channel region. So having gone over briefly the large signal behavior and modeling of the MOSFET, and we're going to quickly review the low frequency small signal modeling of the MOSFET. And this is the model in active mode. And the small signal model is obtained by simply linearizing the IV relationships of the MOSFET's four terminals. So the transconductance of the MOSFET GM captures the linear part of the dependence of drain current on gate source voltage. RDS captures the dependence of ID on VDS in active mode and with a linear term. And finally, we've got the body effect modeled here by this transconductance with the value GS that captures the body effect, and it results in a current that's dependent on the source to body potential. And again, each of these is obtained by linearizing these large signal drain current expressions with respect to terminal voltages. You'll also note here this expression here. The transconductance of a MOSFET is equal to 2 ID times V effective. ID in this case should be distinguished from the small signal lowercase ID here. In this expression down below, the uppercase ID refers to the bias current around which the MOSFET is being linearized. That is the operating point around which we're performing the small signal analysis. Same goes for the value of V effective here. That is the operating point overdrive voltage. Just a reminder of that. Similarly, we can find the value of the small signal parameter RDS in terms of the transistor parameter lambda and the bias current in the MOSFET ID. And then finally, the body effect transconductance GS depends on the operating point of the source to body voltage and the body effect parameters gamma and the Fermi voltage here. You'll see here again that gamma shows up here, and again it's kind of relating the relative strength of GS and GM. But of course GS also depends on the operating point applied. So this expression here is based on the small signal model, and therefore should always be considered approximate, an approximate expression for the transconductance of a MOSFET, but is very useful for developing intuition in analog design, and therefore and can be used to perform some rough calculations for relatively long channel length devices. So you'll see here we're saying that the transconductance GM of the MOSFET is proportional to its bias current and inversely proportional to its effective overdrive voltage. You'll notice that the lambda term here that captures the dependence on VDS is missing from this expression altogether. So implicit in this expression is the assumption that either we're operating right at the border between active and triode operation, because in that case, VDS equals V effective, and we could substitute, we have then, that's the basis upon which we say that the drain current, this is the derivative of the drain current with respect to VGS. Otherwise, there would be extra terms here. Either that, or we're effectively assuming that lambda equals 0, in which case there is no velocity saturation happening. So these are obviously approximations, significant approximations, but again, they're useful for building intuition and knowing the dependencies at play here. Now, it turns out that with a straightforward substitution for the drain current ID, we can substitute in ID equals 1/2 mu NC ox W over L V effective, right? Squared. And so if we make that substitution, you actually end up with the expression shown on the left, in which case V effective now appears in the numerator. So based on the expression on the left, it would appear that transconductance increases with increasing V effective, but based on the expression on the right, it appears that GM decreases with increasing V effective. So which is it? Well, they're both correct. The reality is that, of course, because they're mathematically equivalent expressions based on our simple square law model, the truth is that GM increases if V effective is increased by increasing the drain current and keeping the device width constant. So if you have a fixed device, you're not changing the device at all, and you just crank up V effective, then you've got more current. In fact, the current increases quadratically, and so there's a net increase in GM. However, the expression on the right captures what happens if drain current, better captures the intuition for what happens when drain current is kept constant. So let's say the transistor is held at a constant bias current, and instead, as a designer, you influence V effective by changing the device width. That is, you kind of redesign the transistor. So for example, if you keep a constant drain current but decrease the device width W, then V effective is increased. In that way, drain current is held constant, and as a result, we would see GM decrease. So since in a lot of analog design, operating points are established by constant current sources, actually the right expression is often more useful for design purposes, because we're not usually establishing V effectives explicitly. We're usually biasing with constant drain currents, and then if we effectively choose V effective for each transistor by sizing it, choosing its W over L ratio. Just a reminder that you can also have a low frequency small signal T model for the MOSFET. It looks like this. Just one quick point. Again, I assume this is all background knowledge for you, but just a reminder, not to be confused by the small signal model, wherein it appears that the gate voltage is actually somehow connected to the channel, and therefore current can somehow flow from the gate and then out the source or drain. That's obviously not the case. Just from the physics of the situation, the gate is physically isolated from the drain and source, so you can't have DC current certainly flowing this way. And but the model works out, and it's not inaccurate, because by construction, this value of RS is chosen so that it exactly, the current down here is exactly equal to the current of the dependent source up here, which is equal to GM VGS. Body effects not being shown here. And often a lot of people find that the T model is better suited to a lot of analog circuit analysis because often the source terminal is at small signal ground. So in such cases, the T model, kind of can capture some first order behaviors more intuitively. Now, to capture the high frequency behavior of a small signal behavior of MOSFET, we have to consider all the capacitances at play, and there are many. There's capacitances between virtually every pair of neighboring terminals in the MOSFET. The largest parasitic capacitance is typically the gate source capacitance, CGS, because it includes the capacitance between the gate and the inverted channel region, or most of it. Any AC current flowing through this capacitance, the majority of it will flow in and out of the source when the MOSFET is in active mode. And you see that dependence captured here. So in this expression, you'll see how CGS depends on the area of the gate, W times L, as well as Cox, which is the specific capacitance or capacitance per unit area of the gate. It in turn depends on the dielectric constant of this oxide, typically silicon dioxide, and the thickness of the oxide layer. So this sort of looks like just straight up expression of the area of a parallel plate capacitor, but we've got this 2/3 term here because it's not a simple parallel plate capacitor. You've actually got an inverted channel here, so it's connected somewhat to two terminals. Then you've got this extra term here, COV, which is the overlap, so-called overlap capacitance. That is, it captures capacitance that may arise due to the close proximity of the gate and source region here. Similarly, overlap capacitance arises between the gate and drain, although it's not shown explicitly. You've also got junction capacitances arising all over the place because the channel region is inverted, and you've got reverse biased PN junctions all along the bottom side of the source region, the drain region, and the channel itself. So these are all the capacitances associated with those reverse bias junctions. Another point to make here, which impacts the parasitic capacitances of a MOSFET differently depending on how the transistor is oriented and physically laid out. Another important point to note is that in some technologies, the way transistors are isolated from other neighboring transistors involves introducing a relatively heavily doped region in the sort of body terminal area here to ensure that no parasitic channel is formed between, let's say, this NMOS transistor and its neighbor here. Otherwise, you can imagine in principle, here you've got an N region, and a P substrate. So you might say, well, all it would take is some large voltage to be applied on some wire running up here. And in principle, you might start to invert the channel between the channel region between this drain here and this drain here, between two transistors that are totally, unrelated. So to prevent that from happening, a bunch of isolation measures are taken. One of which is to introduce, as depicted here, a sort of extra insulating layer, and another technique is to introduce a heavily doped layer. Now, this has an important impact on parasitic capacitances because a heavily doped region forms a heavily doped PN junction here, which therefore has a higher reverse bias capacitance. So you end up with a component of the parasitic capacitance of the drain that depends on this, how long the edge of this drain region is, okay? Um, which which may depend on how you lay this transistor out, what orientation you use, and anything you can do to effectively minimize the perimeter of the drain region can help to reduce the so-called sidewall capacitance, which again, it can be dominant even over the capacitance due to the bottom part of the drain junction. There's a similar sidewall capacitance formed on the source regions as well. Here's some review material that reminds you about how the reverse biased capacitance of PN junctions depends on the voltage applied across it. For an abrupt junction, you end up with this inverse square root relationship shown here. So I'm going to skim over this material, but I encourage you to review the corresponding sections of the textbook, especially if you're a little rusty on this stuff, to remind yourself why and how junction capacitances vary with the voltage across them. This material here just reminds us that the inverse square root relationship may be changed to have an exponent other than -1/2 if the junction is not modeled as an abrupt junction. That is, if there's not an abrupt transition between P-type material and N-type material of two different concentrations. So in practice, as you can imagine, the dopant concentrations don't change abruptly with one atomic layer of thickness. There's a gradual transition, and the result is that this exponent in the model of capacitance deviates from 1/2 to sort of -1/2 to more like -1/3, depending on the specific dopant concentration profile. Here's a nice technique. So, because of that, what you end up with for all those capacitances are nonlinear capacitances. That is, if you have a capacitor whose value effectively depends on the voltage applied across it. So, as always with small signal modeling, we can just calculate the value of capacitance at one particular operating point, that is for one particular reverse bias voltage, and use that value to do some analysis. But that may result in some inaccurate estimates when the voltage across the capacitor is actually changing by quite a bit, right? When essentially the signal across that capacitor is not small. So this is a technique to estimate an equivalent capacitance that's a little bit more accurate in situations like that. Effectively, it takes a kind of an average junction capacitance, averaging the sort of capacitance of the junction at its initial voltage, in this case 0 volts, to its final voltage, in this case 1 volt. One approach would be to just take the value of capacitance as the value with 0.5 volts across it, but it's actually more accurate to do the averaging in this way here, which takes into account the nonlinear relationship as the voltage here is undergoing the transition from 0 to 1 volt in this simple circuit. And you can try out this analysis in SPICE, and you'll see that the result obtained using that approximate method is more accurate than a simple small signal approximation by comparing with transient simulation. And this is an example taken from the book. There's the results of the simulation. They can be compared with the calculations in the example above. Okay, so here's a more complete high frequency small signal model of the active mode MOSFET, showing a lot of the capacitances here, and then again adding them to the small signal equivalent schematic. Again, CGS is typically the largest capacitance, but CGD is also important because of the Miller effect in some circuits. And then you've got drain bulk capacitances, which are important because they may load output nodes of various circuits. And just to be complete, there's also a source body capacitance as well. Now, the capacitances that are focused on in this picture here are the ones that arise because of oxides, like silicon dioxide, separating two conductors, and also those that arise because of depletion layers that are formed across reverse biased PN junctions. But especially in very short channel length MOSFETs, the picture is even more complicated than this. I'll just sketch here. You've probably seen cartoons such as the one shown over here on the left often, and they depict nice rectangular structures for the gate and so on. But in very short channel lengths, I mean, there's no abrupt corners when the dimensions are so tiny. So you're more likely to see something sort of like this. You may have a channel region like this. There's drain and source. The gates, it's up here somewhere. It's got a bunch of rounded corners. And then, importantly, and not shown on the left, are a bunch of sort of contact structures. So you have to make contacts somehow to the drain and source. And then those may go to metal wires that are nearby. And so now you can imagine that there are parasitic capacitances arising all over the place, essentially everywhere you have two closely spaced conductors. So between the gate and the contacts, there's also contacts to the gate required, and connecting it to other metal wires. And now between metal wires, you may see additional capacitances. And so all of these additional capacitances come into play importantly, again, especially in advanced technologies where the dimensions are so tiny. And so the layout of the transistors, the choices that are made as to how to route these wires can become or can have an important impact on the high frequency performance of such transistors. So here's just a quick overview of the impact of layout on the parasitics of MOS transistors. So remember, or we can think of the parasitic capacitances that arise in a MOSFET as including two parts. There are those parts that are proportional to the area of the source and drain junctions, and these are effectively due to the bottom of the source and drain regions, effectively these capacitances here, right? So since those are arising because of the reverse bias PN junctions on the bottoms of the source and drain regions, they depend on the area of those source and drain regions when seen, when looked at from above. So that's what's being depicted here, the bottom right corner of the slide. It's effectively a top view of the transistors, which is the way in which an integrated circuit is ultimately designed in CAD tools. You effectively draw the top view of each layer of the integrated circuit. And so shown here in gray are in this case, these are NMOS transistors. So heavily doped N-type regions that serve as the source and drain of the two transistors. And shown in orange are the gates that pass over the heavily doped regions and thereby interrupt them, creating channels that can be turned on and off depending on the voltages applied to Q1 and Q2 gates. So really what you've got here, this gray area here corresponds to the node J1, okay? This area over here corresponds to J3, and this area on the right is J2. And the black squares are metal contacts, the locations where metal is being electrically contacted, connected to the source and drain regions. So, so back to considering the parasitic capacitances of these nodes, there's the portions proportional to the areas of J1, J2, and J3. And when you view the layout this way, you recognize that you might, by looking at the schematic representation of this circuit, think that J3 would have a large area because there's two transistors, and therefore there's two source drain regions connected to J3, one from Q1, one from Q2. But in fact, when it goes to lay these transistors out, especially if the transistors have the same width W, then they can be stacked side by side. And in fact, in this case, there's no other connections to the node J3. So there's no need to introduce the black metal contacts. So because of all that, it allows you actually to make the area of J3 very, very small. Okay. And so it would have less area, and therefore we would expect less parasitic capacitances between J3 and the body region, which, although we haven't shown it explicitly in the schematic, when we fail to do so typically on an integrated circuit, we assume that NMOS body regions are connected to the lowest voltage anywhere in the circuit, or ground, right? Typically ground. So we've got probably the lowest parasitic capacitances between J3 and ground because its area is the smallest. And then we've got the sidewall capacitances that we described earlier. And these, as we mentioned, are proportional to the perimeters of these junctions. All around this perimeter, you will see these isolation structures that isolate the transistors from its neighbor, which can give rise to large sidewall capacitances. So with those portions of the parasitic capacitances are proportional to these perimeters. And again, you see J3 is a very, very small perimeter. It's only these very small regions here that see the isolation structures. We don't have to consider this part as a perimeter of J3 because those are connected to channel regions, right, which will, especially when the transistors are on, will be inverted, and therefore there's a sort of conductive path there, not a capacitance. So this is just an example where the schematic doesn't tell the full story. When you consider how the schematic is translated into a physical integrated circuit, that is the layout of it, you only then are you able to properly assess the high frequency model parameters of the transistor. In this case, sharing the junction region has significantly reduced the junction capacitances. So here's another example sort of highlighting that. I'll just skim over this quickly, but we're considering a transistor. We're trying to consider the layout of a transistor with a specific W and L. So here's source and drain regions, and the metal contacts to each of them are shown in black. And so this is one way simplest way we might expect simplest geometry to realize the transistor with that specified value of W and L. But an alternative, and we can, based on the dimensions of all the junction areas, the gate area itself, right? We can go and find all the parasitic capacitances associated with a high frequency model. Some components will depend on the area of the source and drain junction. Some will depend on its perimeter. But we may then wish to consider a totally different realization of that same transistor. So here we've chopped up that transistor into 10 segments. Instead of one very wide transistor with a width of 10 micrometers, we can have 10 transistors, each with a length of 1 micrometer. That is 1/10 of the overall transistor width. And we simply need to connect, and the result is 10 transistors, and we simply need to connect those 10 transistors in parallel to realize effectively one transistor with the full width of 10 micrometers. And doing that is maybe not as difficult as it sounds. First of all, we just have to short together all the gates. And then we can alternately short together the junctions between these so-called gate fingers. So in a layout like this, we refer to these 10 gate strips as fingers of the transistor. And by alternating drain and source connections, in this way, you realize that you end up with a 3-terminal device that comprises all 10 of these sub-transistors in parallel. So you effectively have now one transistor with 10 times the width, which is the same as the transistor that was shown in the last slide. So here is the gate of this transistor, here's its source, here's its drain. And somewhere around this structure, you'll also have to provide a body contact, of course. So interestingly, it's just simple geometry and arithmetic will reveal that with this layout strategy, you end up with smaller junction areas, smaller perimeter values, and therefore smaller parasitic capacitances. And essentially, that's because we're, by kind of folding the transistor on itself, we're able to reuse or share junctions for 2 fingers of layout. Like you'll see this region here is serving as a drain region for both this finger and this finger over here, right? And so that creates an efficiency. You've really only need 5 drain regions. And so 5 microns of drain region instead of 10 microns of drain region in the previous approach. So that can save, significantly on parasitics associated with the transistor. But again, this insight would be required at the time when you're specifying the schematic. And indeed, any decent version of SPICE will allow you to specify parameters such as drain and source area for each transistor individually. Because the simulator can't read your mind. It doesn't know how you're going to lay out the transistor, so you need to tell it. Having said that, some SPICE simulators do have the facility to make sensible estimates as to what the drain and source perimeters and areas are, and to calculate parasitic capacitances accordingly. But you can't expect them to read your mind. So there's often value in just taking this into account.